Okay, so this PowerPoint is going to now use the structures that we developed in the last PowerPoints for the electrons around atoms and try to explain how they affect an atom's ability to do stuff. As I've said before, structure leads to function. So we're going to look at the atom's functionality based on its structure from the the orbital energy diagram (OED). Came up with two functional models, the Bohr and the Lewis dot structures. Both of these will help us see why atoms behave the way that they do. And we'll start out with the Bohr model. Okay, so first thing we'll do is look at the Bohr model of fluorine and iodine. Okay, so fluorine has 2 energy levels and 7 valence electrons and 1 empty spot. And iodine has 1, 2, 3, 4, 5 shells, and you can figure that out from periodic table. It's found in row 5, and it has 7 valence electrons as well. So what the two have in common is the 7 valence electrons and the 1 hole. That's their structural similarities, and their chemical similarities are they found in the 17th column of the periodic table. They usually have ion charge of -1, 1 minus, and they react with the first element, and they can take 1 electron from the elements in the first column. Okay, so, and actually what we can do is we can relate these to the structure with the chemistry. The difference between the two is they have different energy levels. And what makes them different chemically is they're found in different rows. Fluorine is found in row 2, and iodine is found in row 5. Also, is when both of them interact with elements from the first column, but fluorine does it more vigorously than iodine. Okay, and this is what we're going to try to do, look at, is why does fluorine react more vigorously than iodine based on these two structures here. So here's a couple of notes we can come up from these comparisons. The number of valence electrons and holes is related to the chemical reaction of taking 1 electron. Okay, we don't have to talk about that. We'll talk about that later maybe. But just know the chemical property is related to the number of valence electrons. So we talked about that in the last PowerPoints. The difference intensities of how they react is related to how many energy levels they have, or more specifically, the size of the atom. The smaller atom, fluorine in this case, is more vigorous in the chemical reaction than iodine. Now we're going to see that's not always the case, that the smaller atom reacts vigorously, but in particular, is true with nonmetals, and we'll talk about that. So if something about fluorine being smaller makes it react more vigorously than iodine. And so fluorine is the most vigorous element in the 17th column, then chlorine, and then bromine and iodine. Okay, all in that order. All right, it's already been suggested that in the last PowerPoints that the number of valence electrons is related to the column it's in, and in fact that's one of Bohr's greatest discoveries, is that relationship. We will mostly entertain why this takes why, and we'll look at the Lewis dot structures to explain why the valence electrons are related to chemical structure later using the Lewis dot structure. But for now, what we're going to do is just focus on the atom's ability to do how well to do that reaction, and it's going to be based on its size. And to do that, we'll focus on the Bohr model. All right, so here's a scenario. Suppose that there are a couple of loose electrons flying around. One approaches fluorine, zips by, and the other zips by iodine. As electrons get close, they will feel a tug toward either atom due to the proton's attractive force on them. So fluorine has protons and air pulling on this electron, and iodine has protons pulling on this electron. Our question is, does one atom have a better tugging power than the other, or is there no difference at all? Okay, so to do that, we're going to do an analogy here. Suppose I have two sets of magnets. Here they are, each separated by layers of sheets of paper. 2 sheets here and 5 sheets here. Okay, and I want to know which one of these pairs of magnets is going to have a stronger attraction. Is this north-south going to have a stronger attraction or less than this one over here? Okay, clearly you can see that the one on the left, the one with only 2 sheets, will have a stronger attraction because there's less interference between the 2 sheets of paper. So the 2 sheets of paper add less the more sheets of paper, more interference, and less the interaction between the north and south poles of a magnet. Okay, similarly, an atom with less layers of energy levels separating protons from the outside electrons has a stronger pull than the outside electrons. So fluorine only has 2 layers, like the 2 sheets of paper, and therefore has a stronger pull on the electrons than iodine that has 5 layers in between. There's a term for the strength of pulling the outer or outside electrons, and that's called electronegativity. A definition of electronegativity, which I'll short as just EN, it's a concept, really, that describes the tendency of an atom to attract a shared pair of electrons or electron density towards itself. We expand this to not only attracting a shared pair, but to attract any electrons. So we say that fluorine has a higher electronegativity than iodine. There are relative values of electronegativity as seen in the following table. These values have no units, are not strictly quantitative but good estimates. Okay, so here you go. Here's the table. And we're going to be able to explain the trend though. But notice that fluorine has electronegativity of 4 and iodine has 2.5, just like we predicted. Okay, and what we're going to notice is that as the atom gets smaller, less shells, it'll have a higher electronegativity. So fluorine only has 2 shells and it has the highest electronegativity in this column. Okay, see, it's the same true for oxygen. Oxygen only has 2 energy levels, and it has the strongest electronegativity of everything in that column. So oxygen has 2, sulfur 3, and as the atom gets bigger, the less it can pull on the electrons. Okay, so what we can do is as you go up, electronegativity increases. We're going to explain this tendency in a minute as well. Okay, so again, the reason fluorine has a higher electronegativity is because it is smaller. That means there's less distance between the protons and the outside of the atom. Anything affects the size can affect the electronegativity of the atom. The first effect here that we noticed right now is the number of energy levels. The less energy levels makes the atom smaller, giving it a higher electronegativity. So again, as the trend is the periodic table, the atoms further up have less electronegativity. Actually, should have more less electron energy levels, and thus higher electronegativity. Okay, so the less the energy level, the smaller the atom, the more interaction between the protons and the outside shell. This explains why fluorine reacts more vigorously than iodine. The higher electronegativity, the greater the reactivity, at least for the nonmetals we're going to see. There's a stronger pull on the electrons and thus a stronger reaction. So fluorine can really grab a hold of electrons because the protons can reach out and react better. Okay, now let's look at elements in the same row, particularly the second row we'll work with. And if you look in the electronegativity table, we'll see that fluorine again has a higher electronegativity than any element in that row, with lithium being the lowest, which is on the far left. Fluorine is on the far right. And if we think about this, this is a little bit odd. And why is that? Because all the elements are in the second row and they have the same number of energy levels. So that means they should be the same size and the same interference effect from the layers. Okay, well, apparently not, because there is definitely a difference in electronegativity. Fluorine is 4.0 and lithium 1. But there is a trend, definitely. To the right has the highest electronegativity. To the left has the lowest electronegativity. Fluorine has the highest electronegativity in a row, therefore it's the smallest. But it's not because of the number of energy levels. Okay, let's explore why this is. So let's look at another analogous situation. Suppose I have a bottle that has a rubber band attached to it, okay? And it's attached to a bar. And here's my rubber band, here's the bottle, and the rubber band is holding the bottle to the bar. So what we can kind of say is the bottle is attracted to the bar by the rubber band. If you took away the rubber band, the bottle would fall to the ground. But the rubber band keeps it attached or attracted to the bar. So this arrow represents the pull of the rubber band towards the bar. All right, now let's take another bottle, and what we're going to do is we're going to add another rubber band. And when you do this, what will happen is that the bottle will be pulled closer to the bar. So the increased attraction brings the bottle closer to the bar. So one rubber band kept it out here, two rubber bands brought it in closer. So the more rubber bands, the stronger the attraction. And again, if you add a third rubber band, the bottle will get even closer. So the tendency is the more attractive force, the closer the bottle will get to the bar. Okay, let's see how this relates to atoms. All right, so here's two setup. Protons are kind of like the bar. The attractive force between a negative and positive is like the rubber band, and the electron is like the bottle. And what we're going to do is see what happens as you add more attractive force. We hope that what we'll see is that the electrons will get closer as you add more attractive force. Okay, so let's take a look at lithium, carbon, and fluorine. Lithium has 3 protons, carbon 6, and fluorine 9. Each rubber band, we're going to say, represents 2 protons attractive force on the electrons. So this is this lithium, and there's 3 protons. So there's 3 protons pulling on these electrons out here. And we're not worried about how many. We're just going to say it's pulling on the outer shell. Okay, when you add 3 more protons, that adds more attractive force, and the outer shell and an atom gets closer to the protons. And then finally, when you add another set of protons, the protons will even get closer. The electrons will even get pulled closer because there's even a stronger attractive force. So this explains why fluorine is smaller than lithium, because there's more protons pulling the electrons in. You consider it like a proton pulling force that's pulling on it. So there's more protons per energy level for fluorine than lithium, increasing the attractive forces, making the atom smaller. Since it makes it smaller, it increases the electronegativity. So as you go from left to right in the periodic table, the number of protons increase. That increases the attractive force, making the atom smaller, and therefore increasing the electronegativity. So we have 2 effects here. The first effect is as you decrease the energy level, the atom gets smaller naturally because there's less interference between the outer and the inner. And also you get a cross effect, and that's as you increase the number of protons, it shrinks the atom because there's more attractive force, and the atom gets smaller. So there's overall tendency moving diagonally across the periodic table, where the lowest electronegativity will be down in the lower left-hand corner because they have the less protons and the most shells. And as you go farther up to the right in the periodic table, fluorine, for instance, has the most protons per shell and the least number of energy levels. So the guys up in the right-hand corner will have the highest electronegativity, and the elements over in the left-hand side will have lower electronegativity. And this puts us at a beautiful place. Okay, so let's look back at our reactions when we were talking about chemical reactions. The main driving point of most, if not all, chemical reaction is the principle of oxidation and reduction, where one substance will gain electrons or negative charge and be reduced, while another substance will lose electrons and be oxidized. Now what we can do is have some possible explanation why this happens. Elements up and to the right have a stronger tendency to attract electrons. They have higher electronegativities, thus giving them possibly the ability to take electrons and become reduced. So they have stronger attraction towards electrons, and therefore, under the right circumstances, can actually take electrons. So the elements in the upper right hand corner have a higher electronegativity and have a higher ability to be reduced. The power of electronegativities gives us a reasonable explanation for this. The top right better at being reduced. On the other hand, the bottom left better at being oxidized. And let's take a look at this table. Let's see the relationship between the top right and the bottom left. The top right, we learned these are the high electronegative atoms. They're nonmetals. When they're ions, they have negative charges, so that means they've gained electrons. Kind of makes sense, right? They have high electronegativities. They're found in covalent molecules, and covalent molecules don't lose or gain electrons. And these guys reduce easier than the other elements. Okay. On the other hand, at the bottom left, or basically almost complete on the left side, there's the metals. They have positive charge when they're ions, so they have a tendency to lose, and we can understand maybe why that is now. It's because they don't hang on to electrons all that well. They oxidize easier. And they're found in ionic compounds as positive charges. Okay, so let's put this all together. Elements in the same column do similar chemical reactions, but where they are in the column determines how well they do due to the electron and electronegativity differences. Fluorine grabs the whole electrons better than iodine because it has a higher electronegativity. So it has a higher, it gets reduced easier. Meanwhile, on the other side of the periodic table, elements in the first column lose one electron, usually when they are ions, but francium is the best at it. It has the biggest atom with 7 shells and a small proton power. So francium, the electron that we'll talk about this later, the one valence electron in francium sits 7 layers away from the protons. It's not all that hard to take that electron away for francium to become an ion, a positive charge. Okay, the reaction tendency of a metal is to get oxidized. Therefore, metals with low electronegativity further down the periodic table have higher reactivity. So this is different than on the other side. So on the left side, the metals, the reactivity is determined by how well they lose electrons or a low electronegativity. So the elements further down the table, like as you look in the first column, elements further down, like francium. Francium has the highest reactivity of all the elements in the first column because it's easier. It has the easiest ability to lose electrons. Now, for non-metals, it's the opposite. Reactivity is determined on how good the electronegativity is. The higher up it is on the periodic table, the higher the activity is. So fluorine is kind of like the ultimate non-metal, the ultimate element to get reduced because it has a higher electronegativity. On the other hand, francium is the opposite. It's the ultimate metal with the lowest electronegativity and the most likely to get oxidized. So the two sides of the table have their electronegativities affect their oxidizing and reduction. Metals getting oxidized is what they do, and therefore low electronegativity is a good thing, lower on the periodic table. Non-metals, they get reduced, so higher electronegativity, so higher up the periodic table. Okay, so as we go across the table, we'll see that they'll tend to be all in between. Fluorine is the best at being reduced, and francium is the best at being oxidized, and we get a spectrum as we go to the periodic table. The center of the table, in terms of electronegativity, is where the metals and non-metals meet, and that's that staircase between non-metals and metals. The elements at this staircase are called the semi-metals or semiconductors, or metalloids, and they can act either like metals or non-metals, giving or taking electrons. And this is a really big deal in terms of electronics, like computers and everything we do these days, cell phones and etc. Okay, let's start out with fluorine. Fluorine usually has a charge of 1 minus. So a question would be, why 1 minus? Why not 2 minus? Why not 1 plus? Why not 2 plus? Okay, so I mean, it has to be given. It just doesn't just. Why does it pick that charge? Why doesn't it pick another charge when it's an ion? Okay, now one of the things I want to make clear is that all eight atoms are stable just as they are. They don't need to be ions. Okay, fluorine has 9 protons, 9 electrons. It doesn't have to become a minus charge. It doesn't need to be a plus charge. Okay, it's fine just being a fluorine with 9 protons and 9 electrons. It's stable that way. Otherwise, it wouldn't be there. Okay. It really has no desire to be anything else. And this is one of the big misconceptions that people talk about in chemistry is it's like atoms want to become like something else. No, they are perfectly fine the way they are. But if they are forced to become something else, like an ion, then they will have a choice to be a certain type of ion. And the type of ion that they become is determined by how easy it is to make that ion, or which ion is the most stable in its making. So which atom, in a sense, releases the most amount of energy when it is made. So what we're going to do is compare F minus, F2 minus, so this is F and it's lost, gained 2 electrons, and fluorine plus, which means that it's lost an electron. And we're going to look at which one of these releases the most amount of energy. And that will determine which one is the most stable. Okay, so we're going to talk about forming F minus, an atom with 9 protons and 10 electrons. So the fluorine has to gain electrons. So what we're going to do is look at before and after the parts and see what happens to their energies. Okay, before, fluorine gains an electron, has 9 protons, 9 electrons. There's an equal pulling power of 9 protons pulling on 9 electrons. And then, like I said, there's no reason why fluorine doesn't like to be that way. The key thing is this extra electron. This extra electron is floating around in space, wandering. It's not close to any protons, and because of that, it has high potential energy. It would lower its potential energy if it could get close to protons. Okay, fluorine has a strong electronegativity, and it has a spot to put the electron in its outer shell. Okay, so the electron can go fairly easily into the fluorine. Doesn't mean that it's going to be a good thing, that it's going to release a lot of energy, but so far it seems to work because there's a spot and fluorine has a strong pulling power. After that electron joins the atom, what happens is the atom gets bigger. Okay, the number of protons has decreased compared to the number of electrons. Now there's 9 protons per 10 electrons. And the atom gets bigger. And the original 9 electrons, and actually all 10 electrons, actually become, well, the original 9 electrons actually become a little less stable because now they're further away. So in a sense, the potential energy of the atom, the original atom, has increased. Okay, so far it's not a good thing to gain this 1 electron because this has not actually released energy, it's actually increased its energy instead of decreased its potential energy. Alright, so let's see what happens to the electron. Okay, that extra electron, when it joins the atom, it has a place to go, I said. And when it joins the atom, it gets really close to a proton. And when it gets really close to a proton, its potential energy goes way, way down, and it becomes very, very, very stable. So you have 2 things going on here. First, the original atom gets a little bit unhappy, destabilizes. but the electron becomes very, very stable. And so what you have to do is combine these two effects. And when you do that, the overall effect of adding to one electron and decreasing its energy outweighs any increase in the energy of the fluorine. So when you add an electron to fluorine, it gives off a lot of energy because of this effect here. Okay, now forming cations, positive ions. Okay, so really the thing that made forming anions is that the addition of an electron to the atom stabilizes that electron. Way more than it did compared to the bad effect of the rest of the atom getting a little bit bigger. So the happiness of the electron getting closer to the protons outweighed the unhappiness of the atom getting bigger. Okay. All right. So what we're going to go through here is similar type thing. And really, let's just focus on Fr plus, and we can do the same thing with Fr2 plus, Fr minus. But Fr plus is the easiest in the most energetically favorable form of ion for francium. And let's take a look at why. So francium has 87 protons, 87 electrons, 7 energy levels, and 1 valence electron. And that valence electron is 7 energy levels away from the protons. Okay, so what we're going to do is we're going to knock that electron out. Okay, so how hard is it to knock the electron out? Hardly any energy is required at all because it's so far away. So when you knock that electron out, it'll become more unstable, but not by a lot because it's so far away. So the knocked out electron gains more potential energy, becomes less stable, because now it's been knocked further away from the protons, but not that much farther away. So it doesn't gain a whole lot of potential energy. However, the rest of the atom becomes more stable altogether. Now there's 87 protons pulling on 86 electrons. Makes the atom smaller. You go from 7 energy levels to 6. Okay, so the atom got smaller. So everything gets more compact. All the electrons get close to the protons. It stabilizes that part of the atom gets more stable. So this reaction is going to, overall, the combination of these two is going to give off a lot of energy, or less, more energy than other similar situations of forming the other guys. And it's because the opposite of what happened with the fluorine. And for fluorine, what happened was the losing of energy of the electron outweighed the gaining of the energy of the atom. In this case, it's the other way around, where the atom loses energy, potential energy, becomes more stable, and that outweighs the electron's gain and energy or instability. So this value goes, the stability goes way up for this guy, and this guy goes down just a little. Okay, now you won't hear this explanation of why fluorine is a negative charge probably in your other chemistry classes. Okay, the way that typically this is told is why fluorine has a minus charge, why francium has a plus charge, for other reasons, for other are given other reasons. Okay. So let's look at that, and we'll compare my reasonings versus the other ways of explaining this. So let's look at the common ions and representative elements. Okay, so um, sodium usually has 10, will have 11 protons, 11 and 11 electrons, but it'll have a negative charge, a positive charge when it's ion. So now it has 10 electrons. Elements in the second column have lost 2 electrons, so magnesium has 12 protons, 10 electrons. Aluminum, I told you it has a 3 plus charge, was 13 protons and 10 electrons. So if you notice so far from sodium, magnesium, and aluminum, when they're ions, they all have the same number of electrons. Okay. Now let's look at the negative ions. All right. Chlorine, when it's an ion, has a negative charge. Everything in the 17 column has that. It normally has 17 protons, 17 electrons. When it gains electron, Cl minus, it has 18. Sulfur is in the columns with 2 extra electrons, so it has 18, and phosphorus 13, it has 3 extra, 18. And if you notice, this is that all these guys have the same number of electrons when they're ions. Okay. Now, one thing to notice about this is that when an ion becomes a positive charge, what it does is it has the same number of electrons as the nearest noble gas, which is neon, that's found up in the previous column. Neon has 10 protons and 10 electrons. Okay, the negative ions all have the same number of electrons as their nearest noble gas, argon. The other thing is that when these atoms get their most common ion, the number of valence electrons is 8. Okay, so 2 things stick out. So when they form their ions, they have the same number of electrons as the nearest noble gas. The positive ions have the same number of electrons as the noble gas in the previous row. The negative ions will have the number of electrons as the noble gas in the same row. And what we mean is that they're isoelectronic. And isoelectronic means same amount of electrons as noble gas. Okay, and this is commonly explained as that these atoms have gained or achieved noble gas status. Also, the ions will have 8 valence electrons after they became ions, which we know is the maximum electrons you can put in the valence shell. And this is often called the octet rule. So often what we say, typically in a chemistry class, is they say that atoms want to become like noble gases. That means get the same number of electrons and get a full outer shell. Okay, that's not really what happens. This is an after effect of after the ion has formed. These 2 things. The ions don't form to do either one of these. Okay, these ions form because these are the lowest energy forms of ions there is. Na plus is the lowest ion form of sodium. Na plus is more stable than Na2 plus or Na3 plus or Na minus. Okay, so these are the most stable ions in their formations. After they're formed, we notice is that they have the same number of electrons as the nearest noble gas, and they have a full outer shell. Okay, some problems with this terminology is it's in most chemistry classes this explained that ions become its most common ion so it can achieve noble gas status. All right, noble gases are called noble because they are usually inert. This is the key word, usually. They are perfect in a sense, which suggests that they don't need to undergo chemistry to become anything else. They are just happy who they are. They're the best. They're the kings. Well, they are stable, but not all equal in their stability. For instance, neon is very stable, but xenon actually can react, and this is because it is big and the valence electrons are very far away from the nucleus, and they can react with elements like fluorine. Noble gases can form ions. You can knock the electrons out, but that it actually requires a lot of energy, and if the form is more unstable than a non-ion. Really, the atoms don't try to be like noble gases, but when they do form their common ion will have similar electronic structure as the nearest noble gas. Okay, part of the problem is that we have to be careful when we say atoms become like noble gases. This does not mean that they turn into noble gases. I used to think that, and that doesn't make any sense at all. It just means that the number of electrons are the same. If an atom were to turn into a noble gas, it would have the same number of protons. When fluorine gains that one electron, and it has 10 electrons like neon, but it has the number of protons that fluorine does. So when an atom achieves noble gas status, we mean in terms of its electronic structure. Remember that the maximum number of electrons that can go in the outer shell is 8. That's it. Not because an atom wants to have electrons in the outer shell. It's because of the orbital energy diagram. You can't get any more than 8. That's it. When an atom has 8 electrons in the outer shell, it's either because that's just the way it is, or because it's forming an ion, and that ion is the lowest formation needed of an ion. Okay, now I just want to make clear that there is some validity in the octet rule. That means is putting 8 electrons in the outer shell does stabilize an atom to some degree that I'm not totally sure about. It has something to do with the quantum mechanics that I have above me, okay? And we'll be talking more about that covalent. So I just make sure but that's not the driving reason why. It might be partially why atoms have their negative charges, but why are positive charges the most common charge? But the most common charge is because the formation of that common charge is the most stable of any ion that can form. Again, I am not against saying filling the outer shell or achieving the noble gas status. Okay, if you take another class or you even hear me say it, but mostly it's just a trick for us to help us know the answers. Just like all the elements in column 1 have plus charge. But I want to make sure that you understand the reason why is the lower energy. Okay, so that's it. So this PowerPoint's quite long. I will suggest how to break it up, and when I send the announcement about it, and we'll get a worksheet, and this will go both the 121 and 110. 121 will have more parts to know than 110. All right. Let's talk to you later. Bye bye.